So this talk will be in the Winu-Ngapakarra copper gold deposits. It is quite similar to a talk I've given at New Gen Gold. So I kept the same authors on the author list. You can read them there, but a few people were going to be here, but unfortunately ran into COVID. But I've also have to acknowledge the entire Winu team. It's quite a big team at the moment, and without their enthusiasm and their really hard work, I wouldn't have been able to give this presentation here tonight. They've been really a real great asset. So Winu is located in the Great Sandy Desert of WA. It's about 100 kilometers north of Telfer. Most people probably know where Telfer is. It's quite an extreme environment out there. Like its temperatures in summer can go up to 50 degrees centigrade. The area is affected by tropical cyclones, which often cross the coast at around that area. Basically, we access it generally from Port Hedland via the Great Northern Highway, and then over a couple of dirt roads coming from the north. We also applied for a large amount of tenement around Winu, so you can see in red, and we got a few JV areas in blue and purple there, just to the east of Winu. So we're actually controlling having a very large tenement holding in that part of the Paterson origin, which is largely undercover north of Telfer. So before we started working there was, of course, in early 1970s was the discovery of Telfer. And after that, we had a very intense exploration program over the outcropping part of the Paterson origin. And since then, the northern part of the Paterson origin, which is undercover, actually the only exploration was there in the early days with oil and gas exploration by oil and gas companies. So they ran quite a few seismic lines across the region, and you see an example over there. They defined this sort of basement, Proterozoic basement high that Winu sits on. But to the west of Winu is actually a sub-basin, a Permian sub-basin, which is called the Barnicadi sub-basin. And from the early 1990s onwards, there was exploration by a number of smaller companies, which are listed there, including Venus Metals and Tippa, a couple of other ones. And BHP did a regional air core grid, basically. Between the dunes, they drilled a whole number of air core holes, basically defining rock types in the basement. Rio Tinto entered the Citadel joint venture with Antippa in October in 2015. This is a timeline of the discovery. So we basically have the entering. Citadel JV in 2015. Shortly after that, we started a regional, province-wide sort of interpretation and target generation exercise. In that exercise, we identified a number of other areas, and we applied for a number of other tenements outside the JV. And on a few of those tenements, we had target areas that we did small extra airborne surveys on. And then the discovery of Winu was in the end of 2017, so December 2017, right in the end of the year, in December, when temperatures were actually way over 40 degrees. Ngapakarra, which is like a satellite deposit to Winu, is a gold-rich system, was discovered the year after. And so we had in 2019, we had the first ASX announcement. Maiden resource was announced in 2020, and we've just gone. I think there's just been a resource update in the early 2022, which you can find on our website. I can put it here, but then I have to put all these disclaimers on the slide, and it will take the entire slide. But if you're interested, go to our website, you can find it. But just a little bit about the regional geology. So this is a map from I think from Geoscience Australia. So basically, we're in the Paterson origin. Paterson origin consists out of the rudal complex here, which is sort of recording a subduction event, and Yanina Basin. And the Yanina Basin is it's like a Neoproterozoic sedimentary basin, and it's been folded again during two orogenies. The Miles orogeny at about 8, well, poorly defined. The ages are very poorly defined so far, and the Paterson orogeny. During the Paterson orogeny, you get a lot of granite intrusions, which are around 660 to 600 million years, and the age of Winu sits in these. In the age of Winu is around 660 or 650 to 660, so it sits in that Paterson orogeny phase. Paterson orogeny is a very poorly defined orogenic event so far. Like it's correlated with orogenic events in Central Australia, but at the moment we know very little about it in this northern part of the Paterson orogeny. So when I was involved in the early interpretation, structural stratigraphic interpretation, which led to our target generation, basically the targets we call Folly North, where we put tenements over. So we were focused on actually making a tectonostratigraphic interpretation of the northern Yanina Basin, which is completely undercover. This southern part around Telfer is outcropping, but the northern part is all undercover. So very little was known of this area except for these rare BHP drill holes. And on the basis of geophysics, basically publicly available geophysics and this rare drilling, we came up with this new interpretation. And this is just like a summary of that. That's the main one. That's just a summary. But that was we identified a number of targets on that western edge called Folly North, and then they were renamed to Matembo, and then they were renamed to Winu by the local traditional owners. And so the geology is basically correlate with the rocks are probably correlation to what we call the Lamel group, the same rocks that are around Telfer, including the Malu formation, which is actually the host to Telfer. We think we have sort of deep water equivalents of those, so we don't see exactly the same rocks, but we probably have similar ages. But it looks like we go to a deeper water part of the basin. These rocks are folded into major anticlines and faulted synclines, so the faults actually cut through the synclines. And then basically that's the Miles orogeny, and then you get a later phase of north-south compression, which actually makes domal structures. So it's very similar to what you see around Telfer, but you get similar outcrop patterns. But all the rocks are intruded by these late granites, both magnetite stable and ilmenite stable ones. So you got ilmenite, you got magnetic and non-magnetic granites. And then on the western side, you have this late, this Permian volcanic or Panicani basement, embayment. So it's a later rift basin. If you have a quick cross section through that, you can see the folding in the sequence. We got two sets of mafic sills. One basically tops the sequence at Winu. Another one sits a lot deeper. We recently dated these, and they're the same age as the mafic sills to the south, so around 820. And the anticlines look like they're intruded by these granites. So the granites look like they're intruding into the anticlinal structures preferentially. And Winu, we know there's a sort of just to the south of Winu is a combined magnetic, non-magnetic granite. So it's probably a composite granite intrusion. A little bit about the regional geology. So we know at Telfer, generally the Yanina Basin is described as being very low metamorphic grade, so like lower green schist facies. But when at Winu, we already see an increase in metamorphic grade. So we're in the upper green schist to the lower amphibolite facies. We've got biotite, muscovite, probably a little bit of Andalusite. And then when you in our regional drilling, we actually see that we get higher grade sillimanite, biotite, and then Beneath Metals drill the hole right in the north, and they get sort of granulite, fascist conditions. So and you can see these sillimanite lenses here. They sort of define a lineation. So this looks like a Miles orogeny lineation. So the Miles orogeny so far has been described as an intracatonic event, but I think you get a lot of evidence that we probably have we actually have maybe a major suture zone to the north of the Anketel Shelf. So we might actually have a full orogenic belt again there during the Miles orogeny. But that'll be something for the future and for future studies. But it looks like we're going into a major orogenic belt again. A little bit about the granite. So the granites, they range sort of from alkali granite to granodiorite. I think around Telfer they're mainly late and post-collisional, but I think at Winu you can start to see that they are starting to go become syncollisional again. So as well. So looks like we're getting closer to basically a collision zone or something like that. Yeah, so probably what I want to say there. But, and then regional metamorphism is overprinted by contact metamorphism. You get these big Andalusite porphyroblasts, and like you actually get an Andalusite overprinting sillimanite there. So when we did the regional work, there was basically two orogenesis models for the Paterson, and they were done very early on. They were done by Nicola Golnicht in 1992 and Steve Rowans in 1994. But they're actually very, very useful. They're very good, and they helped us a lot. And one, there's of course the Telfer model, or the Telfer sort of system. But one thing that caught our eye was this little 17-mile hill copper gold deposit, which is the only copper-dominated system in the Paterson. So, and because our aim was actually to find copper rather than gold, this is the sort of style we focused on. And Nikki's sort of model, which is like you can see as an early mineral system approach, basically what everybody now talks about mineral systems, but Nikki's probably had a mineral system approach here already with all the different deposits in a single model. But it's got a lot of features that you can sort of use. You have to be close to a granite, probably the right type of granite. You have to be in a contact metamorphic zone. You have to be in the right stratigraphy, probably the same stratigraphy that hosts Telfer. And then with Steve Rowans, you can see that it's probably you need a major lineament to home you in as well. So you get all the fundamentals of a fairly simple exploration model, which we used. And of course, when I did this work in the early 90s, I was at university with them. But so there's Nikki's on the right there, and Steve is actually Santa, and I'm in the back there. But because they were actually their work was quite secretive, so they didn't present much. I never heard this work in the early 90s, but they were working on this in the early 90s, and I used it. Nearly 30 years later, I used this to generate targets. Anyway, and there was more work done as well. Like another feature is that this deposit was actually a distinct magnetic anomaly, so we sort of knew we had to look for a magnetic anomaly as well. So on the basis of that, so we generated this set of targets on the western edge of the Anketel Shell for the basement high, and you can see that in those days there was 3 BHP drill holes. These were the air core holes. None of those actually went through the cover at that stage. So the cover is, these holes went to about 60, 70 meters, and they didn't go through the Permian cover. If they would have, funnily enough, if they would have continued along the line, they would have been straight onto Winu. And at Winu, the cover is a lot thinner because the deposit is actually a paleo height. So they might actually have hit it if they continued. And then this is the drilling in 2021. So in here you can see the early magnetic target, and then that's the EM target, the more defined EM target in the little green outline. These are the original target outlines that are taken out from the surface. So there's a picture of the drilling in December 2017. So this is a reinterpretation of the tenement around Winu. So about tenement, so basically you have the correlate. You have the Yanina Basin stratigraphy. So I've given that a name of the Winu mine sequence optimistically, and then a hanging wall sequence and a footwall sequence. But they're probably correlating to the Malu formation in the same formation that was Telfer. We're fairly sure that this unit here is the same as the Punta Punta formation. It's like a carbonate ridge, and then over the top of that you got black shales or black siltstone. So and basically, the geology is not that complicated. It's all sort of dipping off to the west, and then you get an increase of folding towards the sub-basin, towards the margin. And you get a couple of big faults, particularly this one, the Phony Devil fault, which actually separates the Winu and the Ngapakarra deposit. And you basically have these composite magnetic, non-magnetic granites, intruding to the north and to the south, and to the south of Winu. So. And it looks like the magnetic phase is actually a little bit later than the non-magnetic phase. So we have an ilmenite stable phase followed by a magnetite stable phase probably. Now, the other thing you can see is the mafic sill, which actually continues, goes all the way from Winu. That's how we trace most of the stratigraphy here. So in Winu itself, like the rocks are pretty monotonous, so it's very hard to actually distinguish different units in the deposit. So a lot of the distinguishing between the different rock units is done by geochemistry. So we use trace elements and stable elements. We use immobile elements to define the stratigraphic sequence. And you can see an example here of the drill holes interpreted according to the stratigraphy. You get this idea of like an anticline or a monocline, quite looking through the deposit quite quickly. That's basically the copper and the gold shells are created in Leapfrog software, and basically you can make these nice images of different grades, and you basically can see that the deposit actually dips off. Most of the deposit dips off to the east, but it's not exactly parallel to the actual plane of that fold. So a lot of people have suggested that, but it's not the case. And the supergene and the hypergene zones are modeled separately. So this is the prospect geology, or the deposit geology. So you can see it's sort of a half dome or a domal structure that is then cut by this Phony Devil fault. It separates it from Ngapakarra here. And actually the orientation of folding at Winu and Ngapakarra is quite different. So this is more like in a northerly trend, and this is more like in a west-northwesterly trend. So the monocline sort of plunges gently to the south. And if you look at the gold distribution on top of the geology, you can see that the gold sort of occurs in a series of like on echelon left stepping lodes, north trending, and that's surrounded by a big halo of low grade mineralization. Ngapakarra, it's quite different. Like the gold trends, the trend is sort of northwest. But, the drilling there is not that dense yet, so it's actually not that easy to identify the exact trends at Ngapakarra. So we probably need to do a bit more drilling there. And then in the south of Winu, we have this sort of east-northeasterly trend, which is trending towards Ngapakarra. So it's sort of linked. It's still probably, we haven't completely closed it off between the two deposits, I think. So so we have this in gold, you have this northerly trend and this easterly trend, which is quite difficult to explain. Like it's really got our heads in initially. How do you get these two vein orientations at the same event? And then the copper is really dominated by this northerly trend. So it doesn't have that east-west trend in the south. It has a little bit, but there's very little copper at Ngapakarra. So copper is really restricted to this on echelon north trending lodes, dipping off to the east. And again, the copper is surrounded by a big halo of you get these high grade lodes, and then surrounded by this big halo of low grade mineralization. So and looking at cross section, so this is the gold. So we go back to the two areas. So the first cross section is in the north here, AB, and then CD in the south over the east-west trend. If you look at the northern cross section, like it's basically a steep, like about 50-60 degrees east dipping lode, lots of breccias. So it's following these breccia systems. And then you have you can see the depth of the weathering. So the weathering actually goes through the Permian. So the Permian is the weathering contact actually cut through the Proterozoic basement into the Permian. So it tells you that the weathering event is actually post-Permian. And we've got about 50 meters of Permian cover and sand cover over the top of the deposit. So there's a tiny little depletion zone actually, you can see there, right at the top of the deposit. When you go to this is the gold, but when you go to the east-west trend, you get much more, although this is still vein-controlled gold. Like, so it's not like what you see at Telfer, which are like reefs. You see a lot more stratigraphic control on the gold. So, the veins are preferentially developed in certain horizons of the stratigraphy. And then you see on the eastern side, the thing is cut off by the Thorny Devil Fault. So it starts to look a little bit like Telfer, but it's still quite different to Telfer. Like you don't have the same. You do have bedding parallels veins, but most of the veins are still steeply dipping, but they're just restricted to one or two stratigraphic units. If you look at the geology, like that's a picture from, that's how the anticline would probably look like if without cropping. Just the host rocks. So what I said before, the rocks are quite boring. Like they're people in the field call them monotonites because they're all these boring sandstones. They're all pretty dense gray sandstones, often very highly altered. But you see very little sedimentary structures, mostly just like uniform, thick bedded sandstones. Few bedding planes you see as well, but you do get the odd good interbedding of siltstone and sandstone. You do get some cross bedding every now and then. You get lode structures. You get what we call Bauma sequences. So it tells you you're in a deep, probably in a turbiditic environment. And you get rip-up clasts as well, like you see here. So that's that's bringing the conclusion that you're probably dealing with these, what they call in the oil and gas industry, they call these deep water massive sandstones, which are very homogeneous, but you basically come off the shelf and deposit in these big deep water environments. Deeper in the sequence, you do get some calc-silicate rocks, so you get some obviously you got some carbonate inclusions, and then now sort of epidote, garnet, kleine Parkstein, and hornblende. You get of course you get porphyroblastic rocks, so you're probably in the contact zone of a granite. These porphyroblasts are always very strongly altered in the deposit, so they always have biotite chloride rims and feldspar or quartz core. But they may have been regionally you see these Andalusite cordiorite porphyroblasts, and probably when they alter, you go to something like that. You also have the pre-mineralization mafic sill. which is basalt to alkali basalt in composition. That sill has been mineralized, so it contains copper and gold. It's also strongly altered, strongly biotite altered, so we know it's pre-mineralization. This is not the sill we actually dated, so we'll probably still try to age date this one, but which would be good. And then the mineralization is cut by later dikes. So these are different composition to the sills, so they're more andesitic and basaltic. And we haven't been able to age date them, but it would be good to age date them, but so far I haven't been able to do that. But they cut through the mineralized veins. Now before I'll just get a quick drink. Oh, sorry. So just going through the different vein types at Winu. So very rarely we see veins that are not mineralized and folded. So they're probably related to regional metamorphism or regional deformation. Probably part of the mild orogeny pre-mineralization. And then the first thing we see of the mineralized system is this sort of stockwork of very narrow K-feldspar, sericite veinlets, and they generally dip very, very flat. They generally have a very flat dip. So these are probably the first, when the granite comes in, when the granite does the mineralization, when it comes in, probably got very strongly overpressured fluids, and you get these, what they call it, superlithostatic or something. And they probably break open the rock, and you form this network, this stockwork of early veins. It's got only weak mineralization associated with, sort of disseminated weak mineralization. And then when you go, these are cut by the first stage of the mineralized system, which are very K-feldspar rich veins, so they're probably high temperature. K-feldspar and biotite, so over 350 degrees probably. And these are generally quite steep dipping. So you have, but they have a variable sort of trend, but a lot of them are steeply dipping and sort of northeasterly trending. And yeah, people call these pegmatitic veins or transitional magmatic to hydrothermal. Probably more, they are probably true hydrothermal veins, but and they're probably the highest temperature veins in the deposit. They've got a little bit of gold. They can have a lot of copper. They can also be barren, but sometimes the copper is very it's distributed very uneven. So you might see a vein that's barren, but it might have copper further down. So and then the main stage of mineralization is these quartz sulphide. Well, it's a whole set of veins basically, with very similar timing. So we have quartz sulphide rich veins, which we here. So we got big blobs of chalcopyrite, but the gold in those veins often sits in the quartz. So it doesn't sit. It may sit in the chalcopyrite, but it's included in the chalcopyrite. But it looks like the gold in these veins actually comes in a lot earlier, and it comes in with bismuth minerals. And these actually, the sulfides will actually, it often looks like the sulfides actually dissolving the quartz, and actually the early gold and the bismuth as well. So it looks like the sulfides actually overprinting this early gold and bismuth system. So we have early gold and bismuth in these veins, and then later sulfides. The sulfides are often associated with lower temperature minerals, like you have calcite, chloride. You get these rims of chloride and often sometimes anhydrite along the sulfides. So you have the sulfides in these veins actually get introduced very late, so they're not part of the initial vein assemblage. And a few more examples. So we got chalcopyrite in the middle of the vein, and this vein is nice that you can see that the alteration halo goes from K-feldspar in this part, and then it becomes biotite in the bottom part. So the alteration is often strongly controlled by the host rock. So you can swap between K feldspar, sericite, biotite, sometimes a bit of chloride, and often you see open space infill in these veins as well. So in this case, it looks like the chalcopyrite is actually filled in open space. So you get euhedral quartz on the edge of the vein. The chalcopyrite is actually filling in the open space in the center of the vein. The chalcopyrite comes in quite late. This is the main trend of veins, so dipping steeply to the east. And now the next one. But the east-west veins have exactly the same timing as these veins. So we see a different vein, the gold rich, generally copper poor, but it's similar in timing to the main copper rich veins. So and in this case, you can see it's a quartz vein with lots of bismuth minerals, and generally that means that you have lots of gold. And so the gold rich veins are generally associated with the bismuth. And these are these veins dipping steeply to the south. In this case, are basically trending, just being subvertical. And then also part of a little bit later, you get these massive sulphide breccias. So you get sulphide rich veins, but you get like just basically breccias full of pyrite and chalcopyrite. In this case, you get just about all chalcopyrite. In there, you preserve some earlier minerals like wolframite and scheelite, and also you get some flow of this sulphide, which they call in Germany they call Proterozoic texture, and then probably associated with the introduction of the sulphide, you get these little fractures and faults that are very rich in chalcopyrite. This is probably the event where most of the chalcopyrite gets introduced, and this is usually a north-south. You can see these reverse fractures. They dip either steeply to the north or to the south-southwest, and so they seem to indicate a north-south compression that you get during and that probably tells you that during the introduction of the chalcopyrite or the copper, you actually have north-south compression. So that sounds like the Paterson orogeny. Then you have a whole set of late-stage veins. So you have late quartz veins that cut through everything. They're probably mainly restricted to the edges of the deposit, so they're not in the center. They've got all sorts of orientations. They're all over the place. You got the dolerite dikes, which actually cut through the chalcopyrite and through the mineralized veins. So that's a very thin example of a mafic dike. And you get a whole set of late carbonate, pyrite, marcasite, sometimes a bit of galena, like you see here, fractures and veins that cut through the whole mineralized system. So this is the end of the the end of the mineralized system. And we don't know anything about the timing of them yet, but this is we did a bit of age dating, and I won't go too deep in that, but we age dated the molybdenite with rhenium osmium, so we got ages of 655 to 658, and then we dated some biotite, and that's probably, biotite is probably difficult, like it might be a reset age, or and that's significantly younger, although that was probably a post-mineralization vein. But I think that age difference is too big, so it's probably a reset. So comparing that to Telfer, Telfer is at 652 to 645 million years, so it's a little bit older than Telfer. And this is just a summary of all the vein types. So we have the stockwork, the early stockwork, which is horizontal and following the bedding. We got the main stage veins, which are dipping to the east. And then we got the K feldspar ridge veins, which are subvertical. Main stage veins dipping to the east. Later quartz veins, dolerite dikes, and then later fractures and and also faults that cut through the mineralization. So one thing we had was, well, how do you explain these two orientations of veining? Because you have the main gold trend, both north-south veins and east-west veins. So, and then the copper trend is mainly just north-south. So how do you explain that? We know copper comes in a little bit later. Like, so we probably start off with a subvertical or a steeply dipping compression direction, probably when the granite comes in, or when an early granite comes in. We haven't proven this granite yet. We don't know if there's granite below Winu, but it might be. And then you probably have your sigma 2 and your sigma 3 are probably quite similar until you form, maybe you reactivate old fracture networks as well. And then when you switch to copper, you're probably your granite intrusion sort of halts a little bit. And you switch back to the main Paterson north-south compression, and you form your copper vein system in a dextral transpressional regime. So that's probably how we see the structural evolution at the moment, how we explain the different trends of gold and copper. But this might still be, people might still argue with this. Yeah, like just a little bit about the supergene overprint. So what I said, the supergene is post-dating Permian sediment, so it's actually coming all the way through the Permian, and it affects the top of the ore body. So we have a slightly depleted zone right at the top. Then we have an enriched zone, which is characterized by lots of chalcocite and some lesser malachite and covellite, bit of hematite stuff, and there's also native copper in there. So we get some beautiful examples of native copper. And then below that we have a transitional zone that goes into the hypogene zone. So before I'll just get another. Dry mouth. So just a bit of a talk about gold bismuth association at Winu. So here we have, so we got beautiful intergrowth of gold, native gold, which in this case is electrum, and bismuthenite, which is a bismuth sulphide. And there's a little bit of native bismuth left there. And there's a bit of chalcopyrite here as well. So generally, when we get sulfides in the veins, when we get sulphide, we see bismuthenite, so we see bismuth sulphide. But if we don't get a lot of sulphide, we see native bismuth. So the native bismuth is quite early, comes in quite early. And here you can see that we got a good correlation between gold and bismuth. This is like the geochemical data set. We've got a lesser correlation between gold and copper. So, which is to a degree is quite good, because you don't want bismuth in your copper, because it actually gives you a penalty. So overall, we don't have a major issue with bismuth, but I'm pretty sure it'll have to be checked. It has to be controlled when they eventually mine. But yeah, there's a very strong correlation between bismuth and gold. And these are very nice images from Hamersley Iron, which we did together with the CSIRO. These are Maya Mapper images, and you basically see that the bismuth in red basically occurs as a cloud in the quartz, and it's then cut by lenses of pyrite and chalcopyrite. So the chalcopyrite and the pyrite actually cut through the cloud of bismuth. And in here you can see that the gold, which is in the very light green colors, is generally associated with the bismuth. So there's not that much gold in the chalcopyrite here, but it's generally sitting in the bismuth. It goes together with the bismuth. So basically telling you the same thing as the geochemistry tells you already. And here again, like this is in reflected, just in transmitted light, you can actually see that all these dark trails are inclusion trails of tiny little droplets of bismuth, native bismuth, and together with gold and meldonite. So, and this is a backscattered image. So you see tiny little droplets of bismuth, native bismuth, gold, and meldonite, and that's cut by later fractures of bismuth, tellura bismuth, and gold as well. And so these are the highest magnification images, and you can see basically these grains are like micron size, the droplets are micron size. And they're either a combination of bismuth and gold, pure gold, or they meldonite, like you see here. Meldonite is basically a gold bismuth alloy, but it's not stable at room temperature, so it will actually, if it gets time, it will disintegrate into gold and bismuth. These fractures of these fracture fills, they contain minerals like geosciite, which is a bismuth mineral with a tiny little bit of sulfur, and minerals like pilsenite and halite, which are basically bismuth tellurides. And they also contain native gold. So you get early droplets of native bismuth with gold and cut by bismuth tellurides. And then finally you get basically this stuff gets included, sometimes included into the sulphides. And when it gets included into the sulphides, it becomes bismuthenite. So basically you get a bismuth sulphide. So it's probably likely that this originally was bismuth and it just got overprinted by sulphide. And these textures suggest that gold at Winu precipitated according to the bismuth collector model, which is a theoretical model invented by a couple of authors, Douglas et al. And Tooth et al. And they basically showed that if you have a hydrothermal fluid that's over 300 degrees and it's rich in bismuth, you actually form a bismuth melt into this hydrothermal fluid. And that bismuth melt, like that can actually, even if you have very low gold content in your fluid, it will actually scavenge gold into this melt. And it will basically, so you have, even if you have only ppb level of gold in your fluid, it will actually, the melt will actually contain significant proportions of gold. And so this is a very effective mechanism to actually scavenge gold from a hydrothermal fluid, but you need a bismuth. And that was also this model is basically shown here, like Amy Cockerton, she showed this in her thesis and in her paper. Basically, you have a vein, a fluid moving, you get bismuth droplets forming, and then either if you have a gold as a chloride or a sulfide complex, gold will actually go into those droplets of bismuth. And if you look at Winu, so we go from native bismuth, so these are the early droplets. So these are basically the initial melt. I think they are basically represent the initial melt, but they contain native bismuth and also generally either meldonite or gold. And then you go towards these later fractures, which contain the tellura bismuth minerals. So you get halite, pilsenite, and you get the geosciites. Now, when you go into the sulphides, you get included into the sulphides, you get bismuthenite. And here you can see that with the early droplets, you always have pure gold or meldonite. When you go into the inclusions and the fractures, you get actually electrum rather than native gold. You get a little bit of native gold as well, but you tend to get electrum as well. And so basically summarizing that in a slide, so you get at Winu, you get your early, basically from a main stage vein. So you get the early formation of the vein, you're probably over 350 degrees and you precipitate K-feldspar biotite. You get K-feldspar and biotite alteration around the vein, probably a little bit of molybdenite. And you get this fluid going through that has these bismuth droplets, which scavenge the from the hydrothermal fluid. When you drop the temperature, you basically precipitate the quartz, and the quartz gets the inclusions of the bismuth, the native bismuth with gold. And then somehow you fracture these veins again. So you either put some pressure on them. You basically cut the early droplets of native bismuth and gold. You cut it by these tellura bismuth minerals. That actually means that you have to have a little bit elevated temperature because tellura bismuth is stable at higher temperature. The temperature goes up a little bit probably in this phase. And then finally, you cut the whole thing with your sulphide lenses. And any bismuth that gets cold and gold that gets caught up in the sulphide basically turns into bismuth. So in Winu, you basically have an early gold system overprinted by a later copper system. So you probably have an intrusion-related gold system overprinted by an intrusion-related copper system. And just putting that in a summary slide. So here we have deposition of the host rocks on probably there was a proto-Anketel fault. It's not the Anketel fault now sits just to the west of Winu. Maybe there was an early fault there that controlled the deeper part of the Yanina Basin. So you got these deeper water sandstones. Then you get your Miles orogeny, sort of east-northwest, west-southwest compression, and you get your folding, your main fold forming. You get probably amphibolite to green shift, upper green shift to a lower amphibolite facies metamorphism. Then you get the Paterson orogeny starting with intrusion of the granites, and you probably contact metamorphism overprinting this, and probably during this stage you probably start getting that horizontal stockwork type vein network coming in. Then you got your gold event with your north-south and east-west trending lodes and veins, probably related to the pressure of the granite coming from the bottom. And then finally, you switch back to your Paterson north-south compression. And that's when the copper comes in a dextral transpressional event, the dextral transpressional event. And at the same time, you form these little thrust faults. You reactivate during that north-south compression. You reactivate the north-south trending veins, but the east-west trending veins are probably reactivated a lot less. So because they're in the wrong orientation to get reactivated. That's why this trend is mainly remains the gold trend, and that trend is a combined gold-copper trend. And that probably relates to the copper, bringing the copper in probably relates to the more oxidized phase of the granite coming in as well. So, and that's where I would leave it. So thank you for your attention.